Welcome everyone to the F1 Gearbox prequel episode. This episode will start off by covering how I designed the F1 Gearbox from limited information that was available, what I got right, what I got wrong compared to the actual F1 Gearbox, and what would need to be changed to machine a gearbox like this for use in an actual race car, and why you may or may not want to do that. So how did I design this gearbox? Well, I don't want to talk about how I designed each and every part, but I want to highlight some of the approaches and lessons learned and how I designed some of the more challenging parts. Initially, I saw this gearbox about a year ago on a random YouTube video. I thought it was the most beautiful gearbox I'd ever seen. The level of engineering, perfectionism, and the attention to detail in each and every part was amazing. I thought it was a real work of art, and so I said to myself, I've got to build a model of that. I was limited on how much time I could work on a computer, so I conducted a lot of research over about a year there, and made a lot of hand drawings of the various parts and pieces for several months. Initially, I was only able to find a few pictures of the gearbox, so I really actually reverse engineered most of the gearbox from just these few pictures that I just flashed up. I devised all the dimensions based on a few key dimensions I was able to find in the FIA rulebook and some various articles about Formula One gearboxes that I had read. Per the rulebook, I knew that the gears had to be at least 12 millimeters wide, and that they had to have center to center of 85 millimeters. I knew reading online that these gearboxes were under 200 millimeters in length. I didn't have an exact length, but that was my goal, was to be under 200 millimeters, and that the clutches and the basket that the clutches are in is around 110 millimeters in diameter. Everything else from there was really just eyeballing and filling in the blanks to try to figure out the dimensions of all the individual parts. So the first thing I did once I had access to Fusion 360 was I created at least 20 complete throwaway proof of concepts around each of the individual parts that I thought was going to be difficult to design, or I had a hard time envisioning in my head how they would fit together. I used these to confirm that all the dimensions would work and determine if the parts would be 3D printable. Once I had kind of my proof of concepts out of the way, I began laying out the overall gearbox dimensions. This first sketch that's up on the screen here is actually the template that allows me to lay out all the parts and pieces of the entire gearbox. It has where the actual rods for the shift forks are, where the shift barrels are. It has the largest gears and the largest gear of both the main shaft and the lay shaft. It also lays out essentially the diameter of the bearings around the lay shaft, and it actually lays out the bolt holes for the actual threaded rods. Now, here's where I made my first mistake with Fusion 360. I began designing all the sub-assemblies in a single file. If I was to do this over again, I would for sure make separate files for the lay shaft and the main shaft and the other large assemblies, all of which reference this initial sketch for layout purposes. As it stands now, I have 16 fully filleted gears and just a huge number of fully modeled parts that I can't really make changes to the early parts of the design anymore. It can take several minutes to recompute a change. If you're interested in designing large assemblies in Fusion 360, you should really check out Wintergatan's channel. He creates these incredible complex musical machines with thousands of gears and moving parts. He ran into the exact same issue I did with Fusion 360 and actually got to work with Autodesk to come up with some ways to improve the performance. So the first assembly I started working on was the main shaft. I initially designed this main shaft based loosely on a design I had found online. I thought it was the same main shaft for all the gearboxes, but I've since found out that this just the 5 spline shaft is actually a Honda specific gearbox feature. All the other ones all use the same number of splines as the lay shaft, but I'd already designed it, so it was a little too late to work on that. But first designed this spline, and then I started off with actually designing something called the gear centers, or at least I call the gear centers. The actual piece with the dogs is identical for all 7 gears. And so to make things a lot easier on myself, and if I have to make any updates or changes, I essentially design one pair of these dogs, actually just by mirroring them, and then I actually pattern out the remaining gear centers. And this allowed me to kind of play with the spacing between the gear centers and try to get it just right, so that as I started designing things like the slider shaft hubs, which go in between these, and then the actual sliders themselves, I could figure out how much space I actually had between each gear to work with, because that was actually probably one of the hardest things to figure out, was how much space I was actually going to have in between each of the gears, so that I could actually get everything in there that I needed. It was a much tighter fit than my previous gearbox. As you can kind of see here, that's actually, there's nothing that has a tolerance over 0.2 millimeters. So it's a very close fit for a 3D printed part. Once I'd actually created this main shaft with no gears on it, I came back and I actually just used a add-in for Fusion 360 called FM Gears, and I created all 7 gears. I aligned them to their particular position, and then I essentially extruded a hole through the whole assembly, or through all those gears. And then as the last step in my actual gears history, if I go on one of these gears here, is that I actually do a merge. I actually usually suppress it there, but I do a merge with that gear center and its gear, so that I can actually export it as just a single STL. With the lay shaft, I took the exact same approach as I had with the main shaft. Of course, it was a lot easier. I actually have separate gear centers for every single gear, and then these spacers are actually patterned out so that it just align the lay shaft gears in the same spacing as the main shaft gears. One thing that is really nice about having this gear center approach is that you can print out test parts, and you only have to just print out that center to try to see if they fit on the main shaft itself, or the lay shaft. This was super helpful because I had to print a ton of different versions with different tolerances to try to get these to work. Once I got them to fit together, the nice part was then all 7 of them were instantly the right size. Okay, next I started design on what's arguably the most difficult piece to design, and that's the actual shift barrels. So what we have here is an actual sketch of the shift point that I essentially use for all the shift barrels, the slot. So I need to do a little bit of explaining so you can kind of have some background into how this works. Each one of these shift barrels or shift drums, whichever you want to call them, has 9 shift points. That means that there's a shift occurring every 40 degrees, because 360 divided by 9. What this sketch represents is actually 3 of those shift positions. So this one here is the start. So you say 0, you go to 40, 80, and then 120. And the reason for this is this circle, which you see a bunch of these circles here, but we'll just concentrate on this circle here, which represents the actual pin that's in the shift fork. Really, the only critical dimension is right here, where it's actually in the center of the shift. The rest of this, from this point to this point of the 40 degrees, isn't as important. So that means you can actually overlap and go into the previous shift point, so that you can lower the ramp angle for the slot. And actually, in this case, we probably could have gone a little bit further, but this is as far as I had pushed it with my design. So the way you actually design this is there's actually a path that you want the pin to follow. And that path is represented by this line, which is the actual horizontal line that it has to follow. So if it's in this position right here, the shift fork is essentially in a no select state or a neutral state. It's not selecting either gear. This position here is essentially, I believe it's 4.175 millimeters from this line up here. And so what we've done is we've actually drawn a line that represents essentially the shift angle. So this is the actual ramping of the shift pin itself. And then we just mirror that over and you get the exact same line going out as you shift back to that non-engagement point. So that's how all of these actually work. I only actually built one of these, and then I'll show you how I actually map each one of these out. But to actually understand how the pin goes through, what you have to do is actually draw a construction circle at everywhere that a pin would collide with a line. And by that I mean everywhere that as this circle is moving, that it would actually hit something and have a critical clearance. So to do that, actually you can see I draw all these out with kind of a square construction line, but then I actually draw these circles in tangent to these lines that have been spread out the width of the shift drum, or sorry, the shift pin, I mean. So this here, this blue path that's lit up, actually represents the path that the shift pin follows. 3 circles represent the shift pin at each of the critical points, and that allows you to essentially design, nice curves and transitions and arcs into this process so that you get, the perfect spacing between the 2 sides of the slot. Now, there's also some additional space that, like, for example, there's actually a little bit of extra space on this side of the shift pin, and that's because as the shift pin's coming through, this is not a critical dimension. This is the critical dimension. This is where all the pressure is because the shift fork is pushing the shift pin back against this as it's being slid. What I've noticed in all the gearboxes is they don't hold a shift fork pin exactly in place. They only get it to the point that it needs to be, and there's a little bit of give once it's actually in that place that it actually needs to be. If you make them too tight, they bind up. There can be little tolerances in the shift fork between the angle that it's actually on the slider, and it can bind these up pretty badly. So if you actually look on the real F1 gearboxes, this particular line here for the slot is actually considerably larger than the actual pin. So what I do from there is actually take that sketch and I place it on a plane that is parallel to a solid that represents the actual shift barrel itself. And then I actually extrude a surface from each of these parts of the sketch and actually have them go all the way through the shift drum itself. Then I use the split faces tool, and I actually split the faces that are here. And so that leaves me with, let me see if I can hide this, a solid that has its front face actually split where I want it to be. And then I can actually use the offset faces tool and pull these out. And that's how you actually get your slot. So once I've completed this, what I'll do is I'll actually come back and I will cut these at essentially, I think it's 80 degrees. So it would be the 40 degrees in the middle and then 20 degrees on either side. So that gives me the total shift point is 80 degrees. I then take that part, and I'll show you in the next step, I do essentially a bunch of manipulation with that part so that I can come up with everything needed to build the shift barrel. Okay, so here's how I actually build the shift barrel itself. As you can see, these are the actual slots that we just cut out in the previous step. And what I've done is I've actually just mirrored that so that I have essentially my selector fork, going left or right, depending on which way you're looking at it. And once I've mirrored it, I just take it the next step further and I actually line these two up. So the way these shift barrels sequence is essentially it's going to shift one direction, and then it's going to have a no select in between, and then it's going to shift the other direction. Once I actually build this all up, I can show you a little bit more. I've actually had to build a whole table to figure out which direction these shifts have to occur and in what order to actually have them be sequential. Otherwise, it won't shift in order. So the next step is I just do some maneuvering around. Skipped ahead there. But that last step I do is essentially, once I get the parts into the positions I want, and they actually overlap just a tiny bit because of the way I cut them, I just do a sweep from this side to the other side, and that gives me essentially the remaining part of the shift barrel, which is the no selection portion of the shift barrel. And then I just do a merge on all those parts, and you eventually end up with a ton of these little parts, one for each of the shift barrels. So I created a bunch of construction planes that were in the middle of each of the shift points, so essentially where the slider was perfectly aligned in the middle, and then I lined up each of these shift barrels with that. Then based on that table that I had created as to which direction each gear required it to shift, I positioned each one of these in accordance whether or not it has to be, it's moving the shift fork this direction, or is it moving the shift fork down in this direction. And then finally, the last bit of positioning is I went through all of these shift barrels, or all these shift barrel parts, and I actually rotate them so that their actual shift point, this line here, lines up with where they should from a sequencing standpoint. So essentially the way this shifts is it's a no select, and both shift barrels are going to be in a no select position, and they're going to rotate inwards. So they both rotate towards the main shaft, and as they're rotating, it's going to upshift. So the first, 40 degrees will be the right shift barrel will select first gear. Then the left shift barrel will still be in the no select state. They'll both rotate again. The right shift barrel will now deselect first gear and be in a no select state. And then the left shift barrel will select second gear. So that was the easiest way for me to do this, was to actually go through, and I would actually walk through based on that table that I had created in Excel and figure out if each one of these shift points aligned as I was rotating it around. Once I had them all aligned and I felt comfortable that it was shifting properly, the next challenge of all this is the shift pins are at a 10-degree angle relative to the shift barrels. So I had to rotate the entire shift barrel 10 degrees, both parts, 10 degrees opposite directions, one going clockwise and one going counterclockwise, so that the shift pins relative to the shift barrels and the shift points would now be aligned. And yes, I did get this wrong several times. So I printed out a test shift barrel, and I had a little mock-up rig, and I would actually go through and try to figure out whether or not each one of these parts actually aligned. And that pretty much wraps up the gearbox design. Things like these holes in the shift drums, I essentially just used the hole tool, made a series of holes around one side, and then I just patterned the rest of it out with circular, and then what is the other type? The rectangular patterns, to essentially copy those holes up, and then I would remove the instances of the holes that would overlap with the slots themselves. These I initially designed because they're more like the real one, and I was planning on potentially trying hydraulics to actually shift this, but I think that's more of a pipe dream, maybe if I have some time, a long time from now. I also designed it so that if it wasn't strong enough, I was going to place metal tubes down the actual shafts themselves so that I could epoxy those in and make them stronger. I also, even the shift barrels, I did the exact same thing in case I needed a metal tube and aluminum tube down them to make them stronger, which honestly they could be a little bit stronger when they're printed out of like the PLA silks. But really that's the gearbox as a whole. It's not that complicated. It's just a lot of parts that replicate, and that you have to kind of figure out how they all interface with each other. That's the hardest part about the gearbox. And then the fact that every single surface, there's just no flat blocky surfaces on this gearbox. Every bit of material that's not needed has to be removed. So it just leads to a lot of engineering of, even the simple parts like this plate on the front that's the input, that there's a ton of time spent, engineering, making sure that there's, ribs going everywhere, that it's all filleted, that it's, chamfered. That just takes a lot of time, and you can really tell how much these F1 gearbox engineers, were working, how hard they were working to try to perfect this design. Well, I think that wraps up this, at least first prequel episode. The video is already getting pretty long, over 20 minutes, so I'll probably cover in the next one kind of what would be needed to be changed to actually, have a practical use for this gearbox. I kind of probably approach it from a couple of directions. One, if you wanted to actually like CNC it out of metal and try to use it in an actual race car, and then also just how would you, use 3D printing, and how strong, what's the best methods, from a 3D printing perspective to make this a strong gearbox. So until next time, everyone stay safe out there. And if you like this video, please hit the like button. And if you want to see more content like this, please consider subscribing. Thanks. Bye.